So as we talked about last time, the phase shift, this delta phi that we have here, we've looked at two different cases. One is the snapshot picture where we can see a whole bunch of waves and we can measure the wavelength. And we talked about the phase being the distance in position that you were as a fraction of the full wavelength, like if I were right here, for example, and I wanted to know how much of the whole cycle where I was in the cycle. Was I at a trough, a peak, somewhere in the middle? But you can also find the change in phase from any 2 points, just like this, using the same thing, finding out the difference in x, so you can say, what is the phase difference between these 2 points? Is it 180 degrees or pi radians? Or, for example, between these 2 points, right? That would be 180 degrees to go from a trough to a crest. Similarly, from the raft point of view, if you're sitting on a raft oscillating up and down, you can talk about the change in phase from 2 different times just by using this equation. Now we often rewrite this, taking advantage of the fact that omega is equal to 2 pi over the period, and so we can write this as omega times delta t, and that's the phase shift. So the omega takes into account the radians, right, per second times second, so we're left with radians. Similarly, we define something called our wave number, k, not our spring constant. This is our wave number, k delta x. This is wave number, and it is 2 pi over lambda. So it's got a radians over lambda in it to give us time over a distance, radians per meter, which gives us our wave number is what it's called, this k. So when you look at equations for waves and you see a k, please don't think spring constant here, because this is the wave number. It is measured in 1 over meters, okay? It's related to the wavelength. So this is the way we can describe this phase difference. And we're going to use this right now to describe how we want to deal with a wave. So wave, again, this is just a snapshot in time. Let's say this is at t equals 0. And so a wave is obviously a function of position, right? This f is now function. I know we're using f for frequency and function, but here it's a function of position, but it's also a function of time. This y, whether you're at the top at x equals 0, t equals 0, or you're halfway down the amplitude at some x position right here, right? That gives you your y value at t equals 0. So this is our wave at t equals 0, but in general, our wave is going to be then shifted over. The way we want to describe this is we want to talk about something that looks like this at hopefully the same shape at, say, t equals 1 or t basically greater than 0 if we want a wave that's traveling to the right like this. So this is still my x and y. So at some point, this point and this point should have the same y values at this new x value and at t equals 1 or 2 seconds. Okay, so our y value our y is a function of x and time, but we can limit this even more because we want to take whatever shape we have at time t equals 0, this snapshot, what's called our wave profile. We want to take our wave profile and we want it to keep the same shape, have this same function, just shift it down. And so we can say what we want to do is we want it to have a phase shift. And there are really 2 contributions to what happens to this, right? So we can have a shift, our y value shifts in the snapshot case. So that would be this, k delta x. And then we can add in this time, the phase shift due to the time. So omega delta t, and to clean this up a little bit, typically we set this so that x 0, the initial x, and the t 0 are both at 0. And so then we say our function y, that's a function of x and t actually has to be a function of kx plus or minus omega t. Now this doesn't seem all that different from this, except that it really limits the types of equations we can use to describe a wave. But this will describe something that's a particular shape, and then watch that shape shift over, either to the right or the left. And so let's look at what it limits and what it allows. Okay, so we're going to look at what equations are allowed and what aren't. So y needs to be a function of kx plus or minus omega t in general. And so let's look at one example. Let's say my equation looks like y is equal to x times t squared. That isn't allowed because it's not in this form. So that's not okay. But if we look at something like this, y is equal to x minus t squared, this is an okay form. It has this functional form where we've set k is equal to omega is equal to 1. You can see it's of this form. It's a function that is of x minus t and then quantity squared. So let's see what this might look like. Turns out not to be a particularly useful wave. But if we look at y as a function of x, again, this is our snapshot. So this is y as a function of x, our snapshot, at t equals 0. To make this easy, that's just y equals x squared. So I have a parabola, which isn't really a good wave shape, but you can make it inverted parabola, and that might feel a little better. Well, let's see what happens at, say, t equals 1. Here's x, here's y. Again, at t equals 1. Well, at t equals 1, when I put in x equals 0, I have 0 minus 1 quantity squared, so that would be a 1. So let's see, that's 1. And then at t equals 1 and x equals 1, I get a 0. So let's say right here, that would be my 0. Then at t equals 2 and t equals 1, that's what we're doing. And x equals 2, I'd have a 2 minus 1 or a 1 squared, and I'm like this. And so I'm back to a parabola, sort of. It's supposed to be the same shape, but you can get a parabola that now has shifted over to the right. So this is something that's moving off to the right, okay? So what we've done is we've taken a shape, an initial parabola shape, and we've shifted it now as the time increases. And as we increase the time more and more, it'll shift off to the right. If we decrease the time, if we went into negative time, we would go the other direction. And so this tells us the beginnings of what our wave equations can start to look like. They need to have this form because in this form, they'll have a shape that can then translate. Probably not a parabola, something more like a Gaussian makes more sense, or a sine or a cosine, but you get the idea, I hope, that this limits the type of function, and then we can have a wave that repeats itself. I should say this presumes what's called a non-dispersive wave. That is, so this would be non-dispersive, which is just another way of saying it doesn't disperse, it doesn't change its shape, it doesn't flatten out over time. So this is a special kind of wave, but it's described by this equation. And so we're going to try to figure out what kind of equations are going to describe the different waves that we see.